Just take a look around you for a second. That glass on your table, the metal in your phone, the plastic of your keyboard, they all seem pretty straightforward, right? But what if I told you that beneath the surface, they all have a secret life, an invisible architecture that dictates literally everything about them? And today, we're going to pull back the curtain and explore that hidden world.
So let's kick things off with a little puzzle. What on earth could a diamond, a copper wire, and a plain old glass window possibly have in common? I mean, think about it. One's a super hard gemstone, one's a bendy metal, and the other is a fragile, clear pane. They couldn't be more different. Or could they? They do share one really basic property.
Yup, you got it, they're all solids. But that simple label hides an entire universe of complexity. The real question, the one we're diving into today, is why? Why are they so wildly different? The answer lies deep, deep inside, at a scale that's almost impossible to imagine.
Our journey into this invisible world really starts with a fundamental battle. It's a clash between perfect, beautiful order and absolute chaos, all happening at the atomic level. You see, the biggest mistake is thinking all solids are the same on the inside. They're not. And the very first clue to understanding them is to look at how their basic building blocks, their atoms and molecules, are actually arranged in space.
Okay, so on one side of this divide, we have what are called crystalline solids. Just picture perfectly organized soldiers standing in a flawless formation. Their particles are locked into a super precise repeating three-dimensional pattern. And this isn't just a small, neat little patch. It's what scientists call long-range order, meaning this perfect pattern goes on and on throughout the entire material.
And get this is what blows my mind. It turns out there are only 14 possible ways to arrange points in a repeating 3D pattern. That's it. These are the Bravais lattices, and every single crystalline solid in the entire universe, from a tiny grain of salt to a massive steel beam, has to follow one of these 14 geometric blueprints. It's incredible. Now, on the other side of the battlefield, we have the amorphous solids. The name literally means without form. The best way to think about it is to imagine taking a snapshot of a liquid and freezing it instantly in place. That's an amorphous solid. The particles are just a jumbled, chaotic mess with no pattern, no long-range order at all. That's why they're sometimes called pseudo-solids. Our glass window from the beginning? A classic example. And this is where it gets really interesting, because this internal difference between order and chaos has huge real-world consequences you can actually see. A crystalline solid, like a salt crystal, has a very specific sharp melting point. Bam! It melts. And if you break it, you get these clean, flat surfaces. But an amorphous solid, like our glass window, just gets softer and gooier as it heats up, melting over a whole range of temperatures. And when it breaks, you get those sharp, curved, unpredictable shards we've all seen. It's all because of that inner chaos. So we've got this huge divide, right? Crystalline versus amorphous, order versus chaos. But the story definitely doesn't stop there. Now we're going to dive even deeper into the world of the orderly, crystalline solids, because even with perfect atomic arrangement, there is a ton of variety. So what's the next piece of the puzzle? Well, it's the glue. It's the type of chemical bond that holds that perfect crystal structure together. It's not just about how the atoms are arranged, it's all about how they're connected. This is what gives each crystalline solid its unique personality. And this basically gives us four main families. First, you've got ionic solids, like table salt, held together by the simple attraction between positive and negative ions. Then there are covalent solids, which are basically one giant continuous molecule. That's our diamond. You have metallic solids, like our copper wire, which have metal ions just kind of floating in a sea of electrons. And finally, you've got molecular solids, like ice, which are made of individual molecules held together by much weaker forces. All right, let's look at ionic solids, like good old table salt. That strong attraction between positive and negative ions makes them super hard and gives them really high melting points. But try to hit a salt crystal and it shatters. Why? Because you're forcing ions with the same charge right next to each other, and poof, they repel and the whole thing breaks apart. They're also terrible electrical conductors because all those charged ions are locked rigidly in place. Next up, covalent solids. Diamond is the poster child for this family. The entire crystal is basically one massive molecule. Every single carbon atom is bonded to four others with incredibly strong bonds, and that's what makes it the hardest natural substance we know. Most are insulators, but then you have graphite, the black sheep of the family. Its atoms are arranged in layers that let electrons zip between them, making it a conductor. It's the same exact element, carbon, but a totally different material, all because of a change in its architecture. And now for metals, like our copper wire. The best way to picture them is a grid of positive metal ions just chilling in a sea of electrons that don't belong to any one atom. And this electron sea is the secret to everything we love about metals. It's why they conduct electricity and heat so well. Those electrons are totally free to move around. It's also why you can bend a wire or a paperclip. The metal ions can slide past each other without breaking apart, because that flexible electron sea holds the whole thing together.
And last but not least, we have molecular solids, like ice or sugar. Think of these like a big party. The guests themselves, the individual molecules, are really strong and stable, but the handshakes between them are super weak. These weak intermolecular forces are very easy to break, and that's exactly why these solids are usually soft, have low melting points, and don't conduct electricity at all. Okay, so we've seen how the arrangement of atoms and the bonds that hold them together shape a solid's properties. But to truly understand something like electrical conductivity, we have to go even deeper. We have to enter the strange and wonderful world of quantum mechanics. So picture this. A single isolated atom is kind of like a one-story house. It has specific floors or energy levels where an electron is allowed to be. Now, when you bring billions and billions of these atoms together to form a solid, it's like building a massive skyscraper. Those individual floors blur together into entire sections of the building, which we call energy bands. These are the zones where electrons can exist. But crucially, there are also gaps between these sections, forbidden zones where no electron can ever be found.
And this is where it all comes together. The energy gap, or the band gap. It's the empty space between the highest filled band of electrons, the valence band, and the next empty band above it, called the conduction band. And get this, the size of this gap is pretty much the single most important thing that determines whether a material will be a conductor, an insulator, or something else entirely. It's the secret sauce behind all of our modern electronics.
Now, just take a look at a conductor, like copper. In a metal, the valence band and the conduction band actually overlap. There is literally no energy gap. Electrons can just effortlessly step into the conduction band and start moving around. It's basically an open superhighway for electrons, which is why metals are such fantastic conductors.
Now let's go back to our diamond and our glass window. They're insulators. And here's why. The energy gap is massive. It's like a huge, impossible canyon that electrons just can't cross under normal conditions. They are completely stuck in the valence band with nowhere to go, so no current can flow. That's why you don't get an electrical shock from touching a piece of glass.
And then, this is where the magic really happens. We have semiconductors, like silicon. Here, the energy gap is just right. Not too big, not too small. It's bridgeable. With just a little bit of energy, say from heat or light, some electrons can get just enough of a boost to jump across the gap into the conduction band. This means you can control the flow of electricity. You can switch it on and off. The simple, elegant principle is the foundation of every single transistor, computer chip, and digital device in the world.
So let's just take a step back and look at where we've been. We started with everyday objects, we dove down into the atomic arrangement, then into the bonds between them, and finally all the way into the quantum world of electrons. It's been quite a ride.
So what's the big takeaway here? It's that everything you see and feel in the solid world, the hardness of a diamond, the conductivity of a wire, the transparency of glass, it's all thanks to this elegant, invisible architecture. From the atomic arrangement, to the chemical bonds, to the quantum energy bands, it all works together to create the reality we experience every day.
Our ability to understand and, more importantly, to control this invisible architecture is what powers our entire modern world. It's in the phone in your hand, it's in the fiber optic cables that connect us, and it's in the spacecraft heading for the stars. The only question left is, as our mastery of this hidden world grows, what will we build with it next?